Will be our topic through the week. So your quiz on Friday will be everything we talk about in regards to vectors, okay? So we'll talk some today. We'll expand on it tomorrow. And then section 4 we'll talk about on I will see you Wednesday for block scheduling. And then we'll quiz Friday. Okay? So to help with the ease of taking notes, so you don't have to write down as many words, because there's a lot of things to write down, I have handed out some closed notes for you to fill in as we go. Okay? So, based on our clip, okay, vectors are directed line segments that have magnitude and direction. Okay? You may remember seeing them as an arrow. When I say magnitude, what is that referring to from the vector? What?
Length.
Is length, okay? And direction, okay, it's pointed in a particular direction, okay? Now, when we talk about vectors being equivalent, that means they're going to have the same magnitude and direction. Okay? Real quick, let's come back to here. Something that we're going to talk about here pretty soon, I want to have some vocabulary. So right next to your first definition, a vector is a directed line segment. Please draw this picture where this is the initial point of the vector and this is the terminal point of the vector. It does matter where this vector begins initially and ends, where it terminates, okay, because that will affect the direction. Okay, and obviously the magnitude, but I'm going to show you some pictures of equivalent and non-equivalent vectors. You can choose to draw them. You can choose to just watch and take it in and think about it. All right? U and V, these are equivalent vectors because they have the same direction and magnitude. Okay? Here, these are probably as close to equivalent as you're going to get. The only difference is they're in opposite directions. Okay? So they're not equivalent vectors, but how else could we describe them? They're similar in what way? Okay, their magnitude's the same. And what is special about their direction? They're opposites. So do you see how those two look parallel? If our direction is the same or opposite, we have parallel vectors. Okay? So these have the same magnitude, but in this case, opposite direction. Okay? These two blue vectors have the same direction, but different magnitude. Since they have the same direction, they would be considered parallel. Okay? And then these two, okay. They have different magnitudes and different directions. There is absolutely nothing in common about them at all, except they are both purple. Okay? My favorite color, by the way. Okay? So let's talk about standard position. Okay? Standard position we've talked about with angles, right? It doesn't change with vectors. Standard position means a vector has its initial point on the origin. Okay? Okay, so all you have to write down on your sheet of paper is the origin. Okay? If we're talking about a vector in standard position, we're talking about that initial point being at the origin. From there, we can think of direction as an angle based on the x-axis, and we'll talk about that here shortly. A lot of what we do with these vectors is going to feel very similar to what we did in chapter 4, which is So let's talk about component form. Okay? Component form is going to be notated like this. And what's going to happen is we are going to take our terminal point and subtract our initial point for each component. Notice how we have an x component and we have a y component. So go ahead under component form, please write down terminal minus initial, and then write down these chevrons right here. So when I ask for component form, you will always be giving me a vector, and we write V for vector a lot, okay? And you'll see these subscripts, okay? You've seen those before. So each vector in component form, they're going to have these chevrons. They look like the less than, greater than sign. We call them chevrons. That's how we know it's a vector instead of a coordinate. And you're going to have a horizontal component and a vertical component. This horizontal component is going to come from the difference in the x's. The vertical component is going to come from the difference of the y's. Okay. Now, before we get to our example, I also want to talk about the magnitude. Okay. Sometimes you'll also see me write a vector as A component, B component. Okay, you'll see both notations. Okay, just so you kind of are aware. Between me and the book, you'll see both of these notations. Okay, so you already told me that magnitude represents the length of a vector. If you need to put that reminder by magnitude, maybe write length. That would be a good reminder. Okay, and we have this funny notation. Do you see this right here? Okay, it looks like an absolute value bar, but it has two of them. Okay, it's just our symbol for the magnitude of a vector. Okay, so let me draw a vector up here in standard position. So if we are in standard position, and this is vector AB, we want to know the length of vector AB. Okay, well, A is the horizontal component, right? And B is the vertical component. What do you think we can use to find the length of that? The Pythagorean theorem. Okay, so we know that this distance here is A, and we know that this distance here is B. So we know that A squared plus B squared would be our magnitude squared. So what you need to know is that the magnitude of a vector would be the square root of A squared plus B squared. It is the Pythagorean theorem, just rearranged so you don't have to do any work, essentially. Okay, and we know that our magnitude always has to be positive because we are talking about a length, so we don't have to worry about the plus or minus when we're solving. Okay, we know that that has to be positive. Okay, so let's look at that example off to the right of the component and magnitude that we just wrote down. We have an example where we have negative 2, 3 and negative 7, 9. So our initial point is negative 2, 3, and our terminal point is negative 7, 9. Okay, we don't even have to graph this. What we care about is what its component form is. Okay, and for component form, which order do we subtract things? Thank you. Terminal minus initial. So for our vector V, we are going to take terminal minus initial for our x's and terminal minus initial for our y's. So what does that make vector v? -5, +6. Oh, no. Yep. We're not getting a whole lot of confirmation.
Yes.
Okay, thank you. So if we were to graph that one in standard position, -5, +6 would be here. -5, +6. Okay, there is vector v. Okay. To find the magnitude of vector v, we would use the Pythagorean theorem. The magnitude is the square root of our horizontal component squared plus our vertical component squared. So the magnitude of this vector would be the square root of what?
61.
61? Thank you. Questions? Okay. Please make sure that when you're talking about a vector, you're using the chevrons. You'll also notice, like on your note sheet, anytime I talk about a vector, like the letter is bolded, we name vectors with letters that are bolded. Okay, so you'll notice that in your homework and in your notes today. Okay, so let's talk about a unit vector. First of all, when we talked about the unit circle, how long was the radius of our unit circle? 1. So a unit vector probably has to deal with length. Okay. Hold on. Okay. So the first thing I want you to write down under unit vector is that we have a vector with magnitude 1. Now, what we are going to do is we are going to force vectors to be unit vectors, okay? We're basically going to take a vector, we're going to keep its direction, but we're going to shrink it down to have magnitude 1. So it's going to go in the same direction, but we're still going to have magnitude 1. And the way that we're going to do that is by taking 1 over the magnitude and multiplying it by that vector. Something that you will see throughout this week, anytime we take a vector and we multiply it by a number, we're still going to be going in the same direction, so its angle is going to be the same, it's just going to be a different length. So what's happening here is we're taking vector v, we're multiplying it by a number that's either going to shrink it or stretch it, but we're still going to be going in the same direction. Okay? So here is our vector. You have it written down to the right there, that very bottom right box. We have a vector 7, -3. Okay? Well, what is the magnitude of 7, -3? Okay? Well, the magnitude is the square root of horizontal component squared plus vertical component squared. What is that?
It's like 7.6.
Well, let's keep it as a radical. Radical 58. Okay. So if we want a unit vector in the same direction, we're going to keep 7, negative 3, but we're going to multiply it by 1 over the magnitude. Okay. And because I'm kind of picky about it, I'm going to ask that you rationalize and go ahead and distribute to both components. So here is our unit vector rationalized, but it's going in the same direction as 7, negative 3. Any questions so far? Okay. This is probably the first new thing you've seen since what you talked about in geometry, but I don't know how much you remember from geometry, so we're just kind of going with the basics. All right. Go ahead and flip the page over. Let's get into some more exciting stuff here. Okay. I am not going to go through all of these properties with you, but just understand that we still have commutative, associative, distributive properties with our vectors. Okay. There is such thing as a zero vector. If we add the zero vector to anything, the vector would stay the same. That kind of sounds self-explanatory. If we take a scalar multiple of 0 and multiply it to a vector, you would get to the zero vector. Okay. Do you notice up here how some things are bolded and some things aren't? Okay, bolded represents vectors. Not bolded represents scalars, so numbers like 2, 5, 17. Okay, so we can take scalars and multiply them to a vector like we just did. Okay, I will teach you on Wednesday how to multiply vectors together. Okay, so let's talk about some of these things here. Okay, we just looked at the properties. If you want to look at them more, I've noted on your sheet that it's on page 421. Where did all of my... Okay, so scalar multiplication, we can take a number and multiply it to a vector. Every component gets that scalar. Okay? Well, what happens if the scalar is negative? What happens to the vector? What would it look like? Okay, so if the scalar is negative, we're going to change direction. Specifically, we're going to be going in the opposite direction. If our scalar is negative, that's going to make our vector go in the opposite direction. Okay. Now, I'm sure if I gave you 2 vectors to add together, you could probably figure out how to do it. But I also want to talk about geometrically what is happening with those 2 vectors. Okay? So when we talk about vector addition, we are going to put the initial point of the second vector at the terminal point of the first vector. And I'll draw you a picture so you can see what's happening here, okay? Okay, so if I'm adding vector u to vector v, Okay, here is vector u. We are going to place the initial point of vector v at the terminal point of vector u. So here's u. I attach vector v to it. And then when we connect these two, there's u plus v. Your book calls it tail to head addition, because we're talking like the tail and the head of the vector. But basically you stack those vectors together, first one and then draw your second one, and when you connect them, that would be the sum. For subtraction, how is that going to change our picture? If I wanted these same two vectors in green and red, but I wanted u minus v, how is that going to change our picture? What's going to happen to v?
Opposite.
Yeah, we're going to have to go opposite, okay? Okay, so if we had u and we were subtracting v, it's essentially the same as adding the negative vector, just like what we talked about when you first learned how to subtract. Okay? And you would still connect those together. Okay? Like I said, the actual addition and subtraction is not going to be the hard part, but I want you to understand what the picture is going to look like. Okay. Anytime we talk about adding or subtracting vectors together, you're going to see this word, the resultant. Okay? Vectors, we have some different vocabulary with. Instead of length, we say magnitude. Instead of sum or difference, we talk about the resultant vector. Okay? I just want you to be aware of the terminology. Okay? So we're going to do a couple examples. You already have these written down. Our vectors are 1, 4, and 3, 2. So first of all, we want to find u plus v. I bet you could already give me what u plus v is without having to draw a picture. What would it be? Yep, 4.
6.
6. Add the horizontal, add the vertical. Now, let's talk about what this looks like on a graph. Okay, so vector u is the vector 1, 4. And from that vector, we're going to add the vector 3, 2. So we're going to go over 3 and up 2 from that spot. So our resultant vector ends up being over 4, up 6. 4, 6. Okay, I put u in standard position, and then I graphed v at the terminal point of that. Okay. Let's talk about u minus v. Well, if we actually subtract the vectors, what are we going to be left with? We have 1 minus 3 and 4 minus 2. Whoops. There. Okay. Geometrically, we have vector u is 1, 4, but we're going to add the opposite of v, so I'm going to actually graph to the left 3 and down 2, because we are now opposite. There's negative v. So you can see our resultant is negative 2, 2. I didn't graph that excellent, but you can be flexible with me. One more example here, 2u minus 3v. One step at a time, people. Okay? If we're talking about 2u minus 3v, we're talking about 2 times the vector 1, 4, and 3 times the vector 3, 2.
Is it minus?
It is minus. I wrote plus. Okay? So first, distribute the scalars through. 2, 8 minus 9, 6. So then our resultant vector is negative 7, 2. Okay? So far, has anything been overly strenuous?
No.
No, pretty basic so far. Okay, which is nice. We're going to keep it basic, and then we're going to do a little bit of trig at the very end. Okay, we really haven't done any, well, we've done the Pythagorean theorem, right? We've done a little bit of trig. Okay, so there are 2 different ways to write a vector. Okay? Number 1 is component form. Number 2 is what we call linear combination form. So what I need you to write down first is that vector I is the vector 1, 0, and vector j is the vector 0, 1. Okay? These are what we call our standard unit vectors. Unit because they are magnitude 1. The vector 1, 0, and the vector 0, 1. They're unit vectors in the horizontal and then the vertical direction. Okay? So another way to write vectors is using these vectors I and j and writing them as a linear combination. So this is component form. Our horizontal component is v sub 1. Our vertical component is v sub 2. So instead of writing this, we could write v sub 1 times vector I plus v sub 2 times vector j. Basically, you take the horizontal component, put it in front of I, plus the vertical component in front of j. Nothing has changed except the way we're notating or the way we're writing our vector. None of the math is going to change. None of the concepts are going to change. It's just a different way of writing our vector. Okay? And I kind of, you don't have to. I like to make my I's and J's bolded because they are the vectors. But I'm not going to require you to get crazy with your pencil lead. Okay. So let's go off to the right and look at that example here. We have an initial point at 5, 2, and a terminal point at -3, -1. Okay? Putting this into component form, we take terminal minus initial, terminal minus initial. So is everyone in agreement that this is the vector -8, -3? Okay. Well, in linear combination form, we would write negative 8I minus 3J. It's just a different form. You still have your components, negative 8 and negative 3, but it's just written all as one. Is there a comma there? No, so you will not write a comma. It's just an addition or subtraction of two items. The first an I, the second a J. I know. Did you know that these are called chevrons?
No idea.
Yes.
Because of the pattern.
I know, right?
Sideways cherries.
Good thing chevron was popular back then.
Sideways
Yeah.
green.
Chevron was really popular in elementary school. It was good.
Okay, so the last thing we're going to talk about, here's where we finally get to use some trade, even your calculators, if you have them. So the direction angle is the measure of the angle between the vector and, here's what you write down, the positive x-axis. Exactly like what it would be if we were talking about rotational angles. I would draw that picture. How might we figure out what that angle is if we know the horizontal and vertical components? We know A, we know B. How do we figure out direction? Ah, what'd you say? Inverse tangent. We know that the horizontal component is A, the vertical component is B, so the tangent of theta would be B over A. Now, first quadrant, perfect. We're going to get the angle that we want no matter what. But your calculator, inverse tangent, will always give you an acute angle. So you are going to have to think about which quadrant that vector lies in. And you need to make sure that you give me an angle between, look at your paper, 0 and 360. No negative angles. I want positive angles between 0 and 360. We're going to do two examples. We'll start off easy here, okay? 3, 4. I'm going to draw the picture because I like the visualization. I do understand that you can figure this out without the picture, but I'm going to draw it anyway. So here's our vector 3, 4. This guy right here is what we're looking for. Okay, so we know that the tangent of theta needs to equal 4/3. So with your calculators in degree mode, to find the angle, you would need to punch in inverse tangent of 4/3. What do you get? 53 point, what? 13 degrees. That is our direction angle. That is the direction that the vector is pointing. Okay, well that was a first quadrant angle. That was easy, right? You shouldn't have issues with a first quadrant angle as long as you keep B over A. That's why I encourage you to draw a picture. Y over X, vertical over horizontal. So let's talk about example B. Negative 3i minus 10j. Which quadrant does that lie in? I'll let you try that again. Okay. So technically we are going to find this angle, but we are going to have to use a reference angle to get there. Oh, that was a terrible triangle. So 3 and 10. I would encourage you to not even worry about the negatives and positives until you're figuring out the quadrant. Okay? Because if you have a negative ratio, your calculator is going to spit out a negative acute angle. That's not a problem, but it really doesn't matter until you get to the quadrant. So what's the inverse tangent of 10/3? So 3 point, give me 2 decimal places. Oh, okay. 73.3 is our reference angle. Is that our direction? We need to be in the third quadrant. If we have a reference angle in the third quadrant, we need to take 180 and then add our angle. So this is more like our reference angle. Our direction angle is actually 180 added to it. So our angle would be what? Okay. That's our direction. Okay. Probably what I'm worried the most about this assignment is you making sure your angle is in the correct quadrant and you remembering how to find a unit vector in the same direction. I'm really not worried about adding. I'm really not worried about magnitude. I feel like those are going to be nice and smooth for you. Please pay attention to your quadrant.